the colloquium. So, Dr. Panini Dasgupta is a postdoctoral researcher at the Ocean Observation Laboratory, Seoul National University, working with Professor Seung Nam. He earned his PhD from Indian Institute of Tropical Meteorology in 2022 under the supervision of Dr. Roxy Matthew Cole. His research focuses on intraseasonal ocean atmosphere variability with a particular interest in the Madden-Julian oscillations and in situ observations of tropical ocean processes, including participation in the Station K mooring program in the Seychelles Chagos thermocline ridge. With this brief introduction, on behalf of IITM and also ECR Hub, I would like to invite Dr. Panini to provide his talk on the title Recent Shifts in the Indian Ocean Wave Characteristics and Their Impact on East Asian Summer Monsoon Rainfall.
First of all, thank you for the introduction, and I am very happy to be back at IITM. It is really a prestigious opportunity to present my ongoing research here. This work is actually the title of this work as recent shift in the Indian Ocean wave characteristics and their impact on the East Asian summer monsoon rainfall. This work is still in its early stage, and I thought presenting here and get your comments and feedback from there. And so this work is with the collaboration of SNU, PMEL, KIOST, IITM, and so these are our collaborators. And before I start my talk, I will briefly tell about the outline of this talk. So first of all, I will say about the motivation which motivated us to look at these things, and then some theoretical perspective of ENSO and IoT, and then followed by the enhanced QB scale variation, quasi-biennial scale variation in the ESN rainfall, and the river discharge, Yangtze River discharge, and the recent shift in the Indian Ocean wave characteristics, their possible cause and impacts. Conclusion. And lastly, I will briefly tell about the SCTR in situ observation, which is called the Station Rama K. So before I begin, so the motivation which motivated us to look at this was the Yangtze River discharge variability. So for your information, I will tell the Yangtze River is the Asia's longest river in going through the China, and this river has a tremendous importance in the Northwest Pacific because the river discharge takes large amount of nutrients here, and that nutrients actually feed this whole coastal population in the Northwest Pacific, including the South Korea, Japan, and China. And you can see that here the primary productivity is very high in the Northwest Pacific because of this river discharge, and the fish catches is also very high in this Northwest Pacific. So over this, the variability in the river discharge, which heavily affect the coastal economy, and as well as there are large impact in the flood and droughts in the coastal region, actually motivated us to look at this Yangtze River discharge variability. So now, if we see how the Yangtze River discharge is connected with the Indian Ocean, so the climatological study have pointed out many like two critical factors, I must say. One is the moisture. So the Yangtze River discharge, which is very heavily connected with the East Asian summer monsoon, that East Asian summer monsoon during the East Asian summer monsoon, the large amount of moisture is actually fed by the Indian Ocean, tropical Indian Ocean. So as the climatological progress happen, this moisture source also changed. So there are another important point is the Western Pacific high here. This Western Pacific high position also shift throughout the season. So here in this figure by Wang et al. 2018, you can see the progression of from June to August, the Western Pacific high, and according the source of the moisture. So the Western Pacific high, when it is westward, that time the Indian Ocean moisture entered the Yangtze River Valley and it created heavy rain. But as it comes to August, the Western Pacific high's position shift further eastward, and the Indian Ocean moisture is no longer that important, and Pacific moisture becomes important. So this is also known as the southwest-southeast source swing. Now, for the heavy rainfall, also, the earlier study showed the Yangtze River floods generally occur due to two causes. One is the East Asian summer monsoon rainfall variability, and another is the tropical cyclones. So, for the East Asian summer monsoon variability, most of the time, the Indian Ocean have a very critical role. And in the tropical cyclone, the Pacific has more critical role. So earlier I was talking about the moisture. So another thing what I have told, that is the strength of the Western Pacific high, which also in fact is connected to the Indian Ocean variability. So this strength of the Western Pacific high also largely show the rainfall in this Yangtze River basin. So this is the interannual variability of the strength, Western Pacific high strength, and the precipitation. So now, the 2019, there was a major flood in the Yangtze River basin that occurred after a positive IOD. And this IOD was very special because this IOD happened without any like concurrent El Nino. So post IOD, this IOD triggered a westward propagating Rossby wave, and that Rossby wave warmed the Western Indian Ocean. This warming triggered intense convection here, and that convection produced atmospheric Kelvin wave. And this Kelvin wave shifts the Western tropical high further westward and help the Indian Ocean moisture to enter the Yangtze River Valley. And this was a very specific case which like motivated many studies to look at the IOD and the Yangtze River flood connection. So later, the other studies also shows the mid-latitude Rossby wave trend in addition to the Indian Ocean create the total variability, like large-scale variability in the Yangtze River basin. So as I told here, the 2019 was a very important IOD event, because if we see the IOD and ENSO, we all know that ENSO and IOD mostly co-occur. The IOD take place during the evolution of the ENSO process. So this figure shows the Nino 3.4 versus the DMI, where you can see there is a straight line, the linear relation, which suggests that when you have a strong ENSO, you might expect a strong IOD. But if you see this 2019 IOD, it was in the absence of any strong El Nino. So that actually triggered many studies to investigate how that IOD happened. And another thing is the IOB, which is called the Indian Ocean Basin-wide warming, that also is, we know that occurs following the El Nino summer, where the whole Indian Ocean is warm. So that also have that sometimes occur with the El Nino and IOD, and that sometimes occurred with IOD. So 2019 IOD also triggered the Indian Ocean Basin mode, which was earlier people used to think that the IOB is only occurred with the ENSO, the El Nino. So this is a very nice study was by the Anila and Nanchil in 2023. They investigated the reason behind this 2019 IOD, the subtropical IOD mode, which triggered this IOD event. Now, as per our understanding, in the Indian Ocean, there are mainly four climate modes which are present, which are seen in the mixed layer. That is the IOD, the Indian Ocean Basin mode, Indian Ocean Dipole, the Ningalu and the Indian Ocean Subtropical Dipole. So in the present lecture, I will mainly talk about this tropical mode of variability, the Indian Ocean Basin mode, and the IOD. But before I go, I will say a brief introduction about the ENSO and IOD's basic structure, because it will help understand why we are seeing the Indian Ocean wave. So the theoretical perspective of the ENSO and the IOD and their similarities and differences. So the ENSO theory in 1997, the Jean et al. Jean 1997 proposed this recharge discharge oscillator, and this proposal came after invention of two major precursor of the El Nino. One is the westerly wind burst. That westerly wind burst happened before the El Nino, which triggered oceanic Kelvin wave, and that oceanic Kelvin wave first warmed the Eastern Pacific. And following that warming, the darkness feedback kicks in and the El Nino develops. That is one. And the second one is the recharge and discharge of the equatorial heat content. So if we take the dominant mode of the equatorial heat content, we find two modes. One is the tilting mode and one is the recharge and discharge phase. So the tilting mode, the first UF is the tilting and the second UF is the recharge and discharge mode. And if we see the time series of those, the two modes, we can see that for before the every El Nino, the whole Pacific is in the recharge phase. And so when the equatorial Pacific is recharged, we may expect a El Nino. And then this tilting mode comes. So the progression of event is like that. So when we have a westerly wind burst, we see the progression of the oceanic Kelvin wave, which warmed the Eastern Pacific first, and then the positive feedbacks. Two positive feedbacks kick in. One is the backness feedback, which we all know that due to the warming, the trade wind weakens and it further increase the SST. And the second is the thermocline SST feedback. So these two feedback, positive feedback, is unstable. It just grows the El Nino. And by the December, the El Nino is in its mature phase. And then the negative feedbacks come, which is the discharge of the equatorial heat content and the delayed feedback by the wave. The delayed feedback, negative feedback by the wave, which is come from the upwelling Kelvin wave here. So in this cycle, we have to know these positive and negative feedbacks which govern this cycle. And also we have to remember that this whole cycle is seasonally phase law. That means the season progression of the season actually helps these positive and negative feedbacks. So the simple recharge discharge model is what I was telling here. The rate of change of the Eastern Pacific SST is function of the temperature and the equatorial heat content, where these positive terms are the positive feedbacks, and the rate of change of the equatorial heat content is governed by the heat content itself, and the Eastern Pacific SST, they are the negative feedback. So this alpha term is the recharge discharge, which is driven by the circulation as well as the wave activity. So this delayed negative feedback by the wave activity is very important after the El Nino. So another thing we must say that in the linear model of the El Nino, there is no asymmetry in the El Nino process. So when we really observe the El Nino, we see there is a high positive SST during the positive ENSO, but the negative ENSO, there is no such high negative anomaly. So that actually comes from the nonlinearity in the backness feedback or the thermocline SST coupling and all. And the F and alpha, which are the thermocline feedback and the research process, actually creates this 2 to 7 years periodicity of ENSO, the time scale, how the time scale are created. But yes, now we will see the IOD. So for the IOD, we will see the similar progression where at first, if the September, October, November is our peak IOD season, we will start from the DJF before the year. And we can see the West Indian Ocean is anomalously low sea surface height, and that is due to the upwelling Rossby wave. And that upwelling Rossby wave reflect as a upwelling Kelvin wave. And this actually create the background condition, very shallow heat content in the Indian Ocean, tropical Indian Ocean, that creates the background condition of the genesis of the IOD. And here, if some favorable wind we get, then this darkness feedback first make the IOD event, and following the IOD event, we get a downwelling Rossby wave, which reflect in the western boundary and again reflected as a Kelvin wave, downwelling Kelvin wave. So we can see that after a positive IOD, we see the recharge phase of the tropical Indian Ocean. Now, similar to ENSO, if we take the first leading UF of the tropical equatorial heat content, we see the two modes. One is the tilting mode and one is the recharge and discharge mode. And we also can see the relation between the wind stress and the DMI shows the darkness feedback, which shows that first IOD anomaly appears, then the anomalous wind appears. The second is the thermocline SST feedback. We can see that the first when the DMI SST appears, after that we see the downwelling Rossby wave initiation. And also we see the recharge of the equatorial heat content following an IOD event. So this three lead-lag relationship shows these things. So recharge following the positive IOD and discharge following the negative IOD. So now we have to understand what are the difference and similarity in the ENSO and IOD. The main difference we see here is the for ENSO, before a ENSO, our equatorial heat content equator is fully recharged phase. But here we see that before IOD, there is a slight indication of the discharge. Whole Indian Ocean is in discharge phase, and then a positive darkness feedback kicks in and it develops the IOD. So these things are very different in the case of ENSO and IOD. And similarities are both have darkness feedback, both have the thermocline SST feedbacks, which are the positive feedbacks and help to grow the anomaly. And there are also the adjustment like the negative feedback, which again bring down the instability back through the recharge discharge process through the wave. So another similarity is the IOD and ENSO both have this skewness in it. So why the IOD cannot be fully described by the recharge discharge? That is because of the external forcing by the ENSO. So it is not purely recharge and discharge process, because ENSO, the wind driven by the ENSO regularly affect these feedbacks, and we don't get this pure recharge discharge oscillator in the IOD. But important point here to note, instead the time scale of the IOD is driven by this wave cycle. So what we can see that IOD takes a special wave cycle, that is the quasi-biennial period. So quasi-biennial period, how this quasi-biennial period comes, because we can see this westward propagating Rossby wave reflected as a Kelvin wave, and then again this cycle of energy between the extratropics and the equator this takes this quasi-biennial period, which is around 14 to 36 months. But if we purely see the speed of the Rossby wave, that is much faster, but we see much slower speed actually, that is due to the wind stress thermocline SST feedback. So now I think I am able to convince you this quasi-biennial period actually captures the main Indian Ocean wave variability. So now I will come to the Yangtze River discharge again, back to the Yangtze River discharge again. So what we see here is from 1960 to 2024, this time series, the green line shows the year average Yangtze River discharge. And this blue line shows the quasi-biennial filtered Yangtze River discharge. And what you can see here, after 1992, like if we just break the period in half, 1992 to 2024, there is a significant increase in the summer monsoon variability, especially the flood years. There are 6 major floods post 1992 to 2024 with respect to only one before. And we also see the quasi-biennial, if we just see the quasi-biennial variability of this Yangtze River discharge or the basin average rainfall, we also see this after 1990, there is a large amount of variability in the river discharge or the East Asian summer monsoon precipitation. And this green line shows the leading mode wave activity in the Indian Ocean, tropical Indian Ocean. And you can see this closely follows this pattern. So basically after 1990, there is a, like we saw a different climate in terms of wave activity in the tropical Indian Ocean. So this actually motivated us to treat this period separately, the 1992 onwards and the before. So this is the different scale, different time scales processes. First is the annual periodicity, second is the quasi-biennial, and the third is the INSO 3 to 7 years. So if you see the variability of the East Asian summer monsoon rainfall, you can see this very dark compared to other time scale. That means all regions have a higher impact of the quasi-biennial time scale. With respect to the other time scale. And if you see the difference between the early and later period, you can also see this Yangtze River basin especially have much higher variability in the later period in the quasi-biennial time scale. I think. So this figure shows the seasonally stratified relation between the Yangtze River discharge and the different climate modes. The DMI means the IOD and the El Nino and the IOB. So in earlier, we see that IOD has a delayed impact on the Yangtze River discharge. So between the early and later period, if you see this delayed impact on the June, July, August Yangtze River discharge, you can see this delay, the time gap between this IOD and the river discharge have a bit shortened. And the most striking difference between early and later period is this amplification of the ENSO and the IOB on the Yangtze River discharge, which was earlier not that much present. So now we see until here that there is a enhanced UV scale, quasi-biennial scale variability in the East Asian summer monsoon rainfall. Now we will look at the shift in the tropical Indian Ocean wave characteristics. So these figures in the upper panel, we see that the sea surface height D20 from ORA S5 and EN4, and this are the quasi-biennial variability, a change in the quasi-biennial variability between late and earlier period. So first thing we note is that there is an enhanced variability in the quasi-biennial time scale. So the wave energy has enhanced in the later period than the earlier period, similar to the East Asian summer monsoon rainfall. And the second thing is the SST, where we see the higher quasi-biennial SST variability in the Western Indian Ocean and the Eastern Indian Ocean in both the ODA S5 SST or ER SST. And the rainfall I already have discussed. So here we see the quasi-biennial variability of these wave processes have enhanced, but there are many waves in the Indian Ocean. So to identify the leading baroclinic modes, waves, the Rossby waves, the leading vertical mode, baroclinic mode, Rossby waves and Kelvin waves, we did the complex EF analysis. So complex EF basically identify the propagating wave modes. So if we see the first complex EF, which shows this Rossby and the Kelvin reflection pattern, it explained 36% in the earlier period, but in the later period, it has enhanced up to the 53%. And this phase angles shows the Rossby wave and the Kelvin wave feed in different region. So I will come into that. So this is a animation. You can see the propagation of the leading EOF mode, complex EOF mode, where here you can see that the downwelling Kelvin Rossby waves are propagating here, and it reflected as a equatorial Kelvin wave. And again, this cycle of this wave energy between the 5 to 10 degrees south and the equator. So this is the typical quasi-biennial scale, and it's the cycle of the energy expended by the first complex EOF mode. So now, if we check the wave speed during the earlier and later period, we see some striking differences. So this green means the eastward velocity, which is in the equator, denoted by the Kelvin wave, and this magenta is the westward velocity for the Rossby wave. So if we take the difference, we see some in the SCTR region, there are very dark blue here, which means the acceleration of westward wave. And in the equator, there is also some red areas, which shows the acceleration of the Kelvin wave. But Kelvin wave, we have to remember, is already a much higher speed than the Rossby wave. So percentage of the change is much less. Now, so that's why we focused mainly on the Rossby wave part. And so the propagation of the Rossby and Kelvin wave of the cycle of the Rossby and Kelvin wave, we also can see as the propagation of MGO in 8 phases. So here you can see this propagation where the upwelling Rossby wave reflect at the western boundary, and then it comes as a Kelvin wave and this cycle. But if we say the difference, we can identify this faster propagation. For example, in the phase 3, you can see already in phase 3, the downwelling Kelvin wave has reflected in the western boundary, and the equatorial Kelvin wave has started, and similar to the upwelling Kelvin wave also. So this acceleration of the wave cycle also can be seen in terms of the phases. If we only focus on the SCTR and calculate the wave speed, we can see that at all phases, regardless the upwelling and downwelling, we see a higher phase speed of the western movement. So this is the phase-wise amplitude and the phase-wise phase speed time series. And here we can see that the amplitude after 1990s have enhanced significantly of this fast mode, and also the phase speed also have produced a higher variability and also higher phase speed, the westward phase speed. So the phase speed also can be calculated in terms of the Hofmüller propagation, where the y-axis shows the different phases and x-axis shows the propagation of the downwelling component. And here we can see that the downwelling component hit the western boundary in phase 6, which was in phase 7 in the earlier case. And in terms of actual phase speed, earlier it is 0.16 meter per second, and it has increased by 0.27 meter per second. So it is almost, the phase speed change is almost by 0.08 or 0.9 or 0.1 meter per second. So this 0.1 meter second is very crucial because it fastened the propagation of Rossby wave by around 1 month. So this 1 month means the seasonal phase locking will be different in that case. So that we can understand through different things. But before that, we have to understand what may be the possible reason around this acceleration of phase speed in the ACTR region. So we know that the pre-baroclinic Rossby wave propagation is highly, majorly related to the stratification structure. And if we see the stratification change in the ORA S5 and the EN4, and check the associated change in the first baroclinic mode phase speed change, we find that phase speed change cannot explain this type of 0.1 meter per second phase speed change, because the associated change should be 1 order less. So we found that this stratification change, here also we can understand, because this figure is very famous by the Shelton et al., where we see the latitudinal distribution of the Rossby wave speed. And between the early and later period, if we only change the stratification, we find a phase speed change by 0.01 meter per second order. But the actual, we get some here 0.1 meter per second or more than that. So stratification change cannot explain this phase speed change of the Rossby wave. So what are the possible other causes that we are still examining? But our idea is either there are some role of the ocean current changes, mean current changes, where we can see the south equatorial current speed has declined between the early and later period. So it is not very well accepted logic, because most of the people don't think that current have a very huge role on the wave speed, but we have to investigate that possibility. And another possibility is the coupling between the ocean and atmosphere has changed, that actually triggered this faster propagation in the second half. So this figure shows the coherence, phase coherence between the quasi-biennial band wind stress curve and the SSH, quasi-biennial SSH. And we can see over the SCTR, eastern SCTR, there is a slight decrease in the coherence, phase coherence. So that means the Rossby wave has no impedance and it can freely propagate. So, but we need to further study this and identify the real reason what caused this acceleration in the phase cycle. So, as I said, we have to understand this phase of the Rossby and Kelvin wave also somehow very tightly linked to this IOD and IOB. So if we take for example, these 8 phases of the propagation of the waves, we can see at different stages this climate mode appears. For example, what we are observing earlier, that the negative IOB happened when the whole basin mode has a low sea surface height anomaly and low thermocline, and that is driven by this upwelling Rossby and Kelvin wave. And we see a IOB-like situation. That IOB-like situation follows by the positive IOD, where we see a positive and negative dipole in the SST, and also the downwelling Rossby wave also intensified and it propagated further westward. And that produced the positive IOB, and then the negative IOD comes. So this whole cycle of this tropical Indian Ocean climate modes actually also tightly coupled with this wave cycle. So that is, we can see from this figure here. And if this wave cycle is accelerated, that means we have a imbalance in the SST budget equation. So here, I will not go to the very detail of this plot, but if you see the earlier and later SST budget terms, you can see that this vertical entrainment and diffusion term greatly produce imbalance in the phase 3, 4, and 5 and 6 here in the later period. So this anomalous warming actually change the SST pattern and also affect the East Asian summer monsoon very heavily. So the progression of wave we can also understand in terms of the seasonal phase locking. So this plot shows the joint probability distribution of the phase-wise propagation, and you can see this shows this higher probability shows the seasonal phase locking between the early and the later period. So if you see the later period, how we can see there is a faster wave cycle, that is you can easily identify by the phase 4 to 5. You can see from phase 4 to 5, this 5 ends around June and July, but in the later period it is this end around May and the phase 6 comes. So there is a faster propagation which is also changing the seasonal phase locking that actually largely affect the heat imbalance. So this is our findings where we have identified few major changes in the tropical ocean wave activity, its intensity, and its phase locking, and its real imprint on the East Asian summer monsoon rainfall. So this conclusion of this work is what we have understood is the time scale of the IOD is largely determined by the cycle of energy between the 5 to 12 degrees south and the equator. Second is the faster cycle may lead to more frequent occurrence of the IOD and IOB state. Third is the faster cycle also change the seasonal phase locking, which could turn the growth and the decay of the IOD and create anomalous mixed layer heat imbalance. And the fourth is that this Kelvin shift in the Kelvin-Rossby wave cycle strength and the speed between earlier and the later period might be driven by the current change or the ocean atmosphere coupling. Ultimately, this shows the result that this shift of the wave cycle is also seen in the QB scale, enhanced QB scale variability in the ESM rainfall and extremes. So from the theoretical perspective, we must say this study highlights the importance of the delayed negative feedback driven by these wave adjustment processes. So before I finish, I will just say about few words about the SCTR observation. So as we have seen, the SCTR is very crucial for this large-scale baroclinic waves, and this where I'm working in Seoul National University, they did this observation called Rama K subsurface mooring in the SCTR. So it first deployed in 2019, and from there on, they have this subsurface observation, which actually complement the nearby surface Raman buoys around the SCTR. So there is a long time series and is available online in the Ramake website, where you can find this daily very good observational details of this wave activity in terms of temperature, salinity, and many things. And these are the mooring line design, where you can see the which depth of in which depth the instruments are there, and so this is a very valuable resources you can try to look into. So thank you very much.
Thank you, Panini. Thank you for sharing your interesting research. Let's open the floor for discussions.
I have a very trivial question, maybe known to everyone. What does ACTR stand for?
Seychelles thermocline region, the way Seychelles Chagos thermocline ridge.
Seychelles Chagos thermocline ridge.
Seychelles Chagos.
You can show the
Can
location.
you show that on the map?
Okay. So this is the Seychelles Chagos thermocline ridge. Maybe. So this region is the box region where the thermocline is very sensitive. Thermocline and SST are very tightly coupled. So any movement in the thermocline is easily reflected in the mixed layer because they are very close to each other.
Okay, thank you.
Yeah, Marini, it's a very interesting talk. I'm just, this is from observation, what you are, that theory or hypothesis or theoretical study has been done using the observation. So it will be very interesting if you see the status of the present climate model. Whether present climate model able to capture these waves, or where is the difference? Means where is the deficiency in the model? Because QB is very important in our institute. Also, people are showing that how it is impact on the particularly interseasonal oscillations. So this is very important for the SMR, definitely. But where is the problem in the model? Whether model able to capture these waves correctly as you have seen in the theoretical understanding? If yes, then fine. If not, what is your hypothesis? How we can improve the models? As you are talking about the discharge, whether the river routing is important for the ocean model, I am not expert on that. But this is my views on the development perspective of the model, where we stand and how we can improve that. Thank you. Thank you.
Thank you. I will definitely.
Hi, Panini. Thank you for the nice presentation. We know like Seychelles region is the region where SST and thermocline are strongly coupled. That's the only region in the Indian Ocean the coupling is very strong. So and you are finding like the phase speed of the Rossby wave have been changed. So is it associated to the ocean? Are you finding any changes in the coupling between the wind, ocean and atmosphere? Is it that driving that, or Indian Ocean warming is having any role
Yes.
in this?
Actually, like we are still looking into that, but our hypothesis, we have not been able to identify the exact reason why the phase speed acceleration is observed. We just knew that the stratification is not the key reason. So it either due to the coupling, which maybe act as a positive feedback, because we here see that this phase locking with the seasonal cycle has changed. So we have the phase six of the propagation is occurring at the later stage, which was not in the earlier stage. So this seasonal phase locking change means the coupling will change, and that have a role in the heat imbalance. And we have I think Soon et al. One recent studies which shows the recent increased occurrence of the early positive IOD. So they
Exactly, that was my point. Do you find any change in the seasonality of the IOD?
Yes.
This must be because your wave propagation speed has increased.
Yes.
So that must definitely change the seasonality and the triggering and the total seasonal cycle of the IOD itself, right?
Yes.
Yeah.
We tried to argue in that point that this early POD is occurring due to this changing.
Because many events like 2019, 2023, all of them, especially 2019, occurred very early.
Yes.
Right? Yeah. Okay.
Hi, Pani. Thanks for coming here and presenting this. So I had you had one plot with, it showed two SST products, ERSST and I think OSST or had ISST. That was a difference. So if you look at the South Indian Ocean, it's totally different between these two products.
Yes.
Yeah. So I mean, I just want to know, using different data products and all, and that will bring a lot of uncertainty in some of the results that you might be showing, right? Especially, I don't know how the SCTR region is, but okay, so you looked at late and early periods. And for example, if you are connecting it with IOD, QB and IOD and so forth, the number of samples that you might have for IOD and all might be quite few, right? I mean, how does that have a bearing on on the results that you are showing?
So the first point, which was this Southern Indian Ocean variability, I also figured out there are large there is mismatch between the different products. For example, the second propagating mode, which shows the subtropical waves, that is hugely different in different product like EN4 and the ODA S5.
Oh, is it so?
Yes, yes.
Okay.
So they are very different. So, but for the tropical modes, if you see the SST, if we just focus on the 15 degrees south to 15 degree north, that is more or less all the product agree to each other. So that's why the first mode we have focused on rather than the other modes.
Is it because maybe because the variability is low?
That,
yeah. Okay.
Any other questions? If not, let's thank Panini for this interesting work and sharing his interesting research. Thank you, Panini.